So now we have almost everything we need for the trait bonus system to work, but we do need to add modifiers to the mix to make sure that we can actually have any effect on the gameplay. We did a version of this in the Slay the Spire course, but I want to do it slightly different here, so maybe you can learn something new if you completed that course as well. In a sense, it will be pretty similar as we split the whole thing into 3 different levels. We'll have the ModifierHandler, which is the higher level thing. This is the node that will be attached to the battle unit. This needs to be a part of the life cycle. It needs to be a node so we can reference it. So if we press Ctrl-Shift-O and search for battle unit, this is what we currently have for the battle units, and the ModifierHandler needs to be a node so we can communicate it. It can be a part of the games and the node's life cycle, and we can have access to the usual advantages that we get from using nodes. Now the middle level will be the modifier, which is one specific piece of data or property that can be modified to a different value. In terms of the battle units, if we search for Bjorn, for example, and double click on it, we have data like max health, max mana, ability power, attack damage, attack speed. All of these values are ones that could be modified by a modifier, right? It's really up to you which ones you want to make it so it can be modified by external sources. But in the context of this genre or this game, what makes sense is that most of these can be modified, right? So one modifier corresponds to one specific value that can be modified. And on the lowest level, we have ModifierValue, which is one instance of modification applied to a modifier. What does this mean? For example, we attach a unit to Bjorn and it adds 5 attack damage, right? So to the attack damage modifier, we append a flat +5 value as a modifier value. And these can be stacked on top of each other and are not dependent on other modifier values, so we can have a trait bonus that gives you 20% attack speed or attack damage boost, right? And those are, again, new modifier values that are added to the corresponding modifier, in this case the attack damage one. In this project, what I ended up with is 3 different base classes for the 3 different levels. It might not be the best solution in terms of mixing it that much, but I think it's a good mix between the advantages of the different base classes, and also it's a great learning experience. So we'll talk about the advantages and disadvantages for using these, but for the highest level we have to use a node, so we have to have a modifier handler attached to the battle unit so we can use it in the project. Now this is something that can be reused pretty easily across projects. So I'll add this to the components folder even though we need all 3 of them to work. I still think it's a great reusable system. If you want to, you can create a different folder for them. I won't in this case, but you can. So let's create a new script and we'll start at the lowest level with the modifier value, which will inherit not from the node class, but from the resource class. So these modifier values will be resources we can create and store on the disk. So let's click on create and double click on modifier value to open it up in the script editor. And this will be the simplest one. So I used a bit of trickery here. So this will not just be a class name, but also it will be a tool script, which means that the code we type here will be run inside the editor as well, not just the game. And what we do first is we'll define an enum. So there are 3 types of modifier values. It can be a percent-based modifier, it can be a flat modifier, and I also introduced the 0 modifier for this project, which is, again, a change for the better, I think, from the system I used in the Slay the Spire course. Now, for the export variables, we have a type enum, where we can pick which one we use, percent-based, flat, or 0. Then we have a float for the percentage value. We have an integer for the flat value. And we also have a source, which is a string. And the source is sort of an ID, which tells the system where do we have this modifier from. This is important so we can stack the same bonuses and modifiers coming from the same source. Now the reason why we use a tool script here is because we want to override the init method. We cannot use ready here because we use a resource, and resources are not part of the scene tree. They don't have a node lifecycle. So we can use this init method instead, which is sort of like a constructor in other languages. If we press and hold Control and click on it, this is called when the object's script is instantiated, when it's initialized in the memory. In terms of resources, this is when we create them in the file system doc, and the script gets attached to it, right? And what we want to do is we set the resource local to scene property to true. And this is available for all resources. And if I hover over it, it says that the resource is duplicated for each instance of all scenes using it. So if for whatever reason we were to modify one modifier value that is stored on the disk, it wouldn't modify all the other ones. Here, this is not strictly needed, but I think it's a safeguard. So we usually want to make sure that all the modifiers in the game, even if they come from the same source, are independent from each other, so they cannot be changed and they don't introduce unexpected changes if we were to change that resource. But this is debatable. I'm still not 100% sold on this. If we don't include this part in the script, then we don't need a tool as well. So what this essentially does, you'll see, is when we create a new resource, this checkbox will be automatically ticked in the inspector panel on the right hand side. For now, I'll leave it as is. And for debugging purposes, what's really useful is to override a toString method. And we can just show the type, which of the three we used for this modifier value, what the source of it is, what percentage we have for it, and what's the flat value, right? So we have all the information available to us on the output. This is pretty straightforward. We can save this with Control S. And that's all we need for modifier values. Again, this is just one specific modification we can make. Right? So far, so good. And this is a resource, so we can tweak and create these from the inspector, right? Now, if we go back to our components folder, right-click on it again, and create a new script, the next level will be the modifier, which represents one instance of a modification. Again, this can be the max HP of the unit or the attack speed or something like that, right? In the ModifierValue course, for the base class of this, we use the node as well. So we had this nice little node representation. Under the ModifierHandler, we had all modifiers available, and the modifier values themselves were nodes as well, I believe. Now, in this case, I'll use the RefCounted class instead, and we'll talk about why in a second. Click on Create, and double click on the modifier class to open it up in the script editor. So what is this RefCounted class? It's sort of like a resource, but without having the added advantage of saving it on the disk. So these are basically data holding objects that don't need to have their memory management handled by hand, right? Reference counting is a technique that is used to keep track of how many other classes reference that specific object in the game or in the memory in this case. And if there is no reference to it, then we know that it can be deleted safely, right? In other languages like C++, you have to manually handle memory, right? So when an object is no longer needed, you need to free the memory that was allocated for it. So reference counting is a technique you can use to avoid having to do that. And these are not nodes because they are not added to the scene tree, but not resources saved on the disk either. So these are just objects stored in the memory that we can use the same way we can use resources, but we just don't save them on the disk, but they sit in the memory instead, right? And if you think about it, we don't really want to save these in the disk because we just sort of want to create that, right? We just want to create one modifier for the AD, the AP, and we don't really want to configure anything with them besides adding them to a modifier handler for the HP, the mana, the AD. So the reason why we use the RefCounted basically is because we don't want to configure them in the inspector, but we don't want to create a nodes overhead either. So we can use this RefCounted instead, provide a custom class name, and we can still define signals so it behaves pretty much the same way as a resource would, minus storing it on the disk, right? So we'll have a signal when the modifier changes. Then we can have an enum for all the types of modifiers we can create inside the game. In this case, we'll have these ones defined for the units, and we have no modifier. Then we'll have to have member variables. So you can't really have export variables for RefCounted classes. These are objects stored in the memory, so we'll have two member variables. One will be the type, storing which kind of modifier that object is. And one will be the modifier values currently attached to it. And this will be an array of modifier values. So again, using the same example, I can have plus 10 AD from an item and also have plus 10% AD from a trait bonus. And if another enemy uses a blind ability on me, which stays there for 5 seconds, let's say, then I have a temporary modifier value that overrides everything and decreases my AD to 0, right? So all these different types of modifiers that can be there will be stored in an array. Now, just as we can do for resources, we can override an init method. And in this case, what we want to do when we create a new modifier from code is that we want to pass in a type to know which kind of modifier we want to add, set the type member variable to that new type, and initialize the values array with an empty array, because when we create a modifier, no modifier values will be automatically added to it. Again, this is like a constructor in other languages. And if we press and hold Control and click on the init, I was hoping to see an example here, but we only get a text. And it says it's called when the object script is instantiated, oftentimes after the object is initialized in the memory, through object.new in GDScript. So when we create a new modifier, this is the method that will be called. And if it's defined with required parameters, like we did with the type, the object with script may only be created directly. This essentially means that when we create a new modifier, we have to type modifier.new, and in the parentheses, we have to specify what type of modifier we are creating, which is exactly what we want in this case. And a super useful method is, of course, getting a modifier value, right? So if we want to check whether a source is already applied, for example, to a modifier, we'll have the source as a string, as the first parameter, and we return a modifier value. We iterate through all the modifier values, and if there is a value with the same source, we return that modifier value, otherwise we return null, indicating that there is no such modifier applied to this. Of course, we want to be able to add new values to a modifier as well, and adding new values means that we pass in a modifier value resource as a parameter, and the first thing we need to do is we call this getValue method we just created, to see if it's already there or not, right? So we grab the source from the new value we want to apply and see if we already have an existing one or not. And these two cases need to be handled differently. So if there is no such modifier value yet, then what we do is we duplicate the resource and append it to the values, then emit the change signal because there was a new value added. Otherwise, it means that we already had that modifier applied with the same source. In this case, the only thing we do is we update the existing modifier values, flat value and percent value properties to the new ones, because it might happen that the same source that we applied is a higher level modifier. Let me give you a specific example for this, right? So let's say we have a trait that applies bonuses which boost all the units HP and attack speed. And the more time elapses in the battle, the more bonus they provide. So it's a stacking bonus, like let's say in every 5 seconds elapsed in the combat, you get 5% bonus on your HP and on your attack speed. Now every 5 seconds, we'll call this method to reapply from that, let's say Vikings do this, right? So the source will be Viking trait. And every 5 seconds, I reapply the same bonus, so there will be an existing modifier value with the same source, Viking trait. But every 5 seconds, I want to update the flat value and the percent value, whichever the bonus uses, to this new value, because if it's the first 5 seconds elapsed, it will be 5%. But if 10 seconds elapses and I call this method again, then I want to override this value I had with the 5% to 10, right? This is an edge case we handle here. Hopefully that makes sense. Again, if we change that value, we can emit the change signal. And if we can add new values, we can also remove existing ones. And it will be pretty straightforward. We iterate through all the values. If the source matches, we call array.erase, which will remove that value from the array and emit the change signal. We'll also provide a utility function called clearValues, which removes all the modifier values from this modifier with array.clear, and then again we can emit the change signal. And probably the most interesting method is this getModifiedValue. This is what we can rely on when we want to calculate the actually modified value that we have. So if we have the base attack speed of 1.5 and we have a bunch of modifier values, this is the method where we calculate the end result, right? So in order for this to work, we need to have a base value that we start from. In some cases, it might be an integer, but it's better to use a float here because when we apply percentages, it will definitely be a float. So the flat result that we have starts from the base value, and the percentage starts from 1.0, which means that we start from 100%. This is what we have. So at the end of applying everything, we'll return the base value, the flat result, multiplied by the percentage. So if we have no modifiers, this means that we have 5 as the base, and 5 times 1.0 is 5, right? So if there are no modifiers applied, then we'll return the original value. Now the order really matters here. So if we introduce a new 0 modifier, we need to check if we have one, because if we anywhere in this have a modifier value which has the type 0, then we can return 0 from the method immediately, because this overrides everything and says that, okay, I don't care what the base value or any other values were, this will be 0. But if there's no 0 modifier, then we need to check for flat modifiers first. Those are usually applied before we deal with any percentages. So what we do is we iterate through, check for the flat value type, and add any flat modifiers to the flat result we have. This can be negative and positive as well. And finally, we apply the percentage modifiers. And what we do, again, we'll have floating point numbers where 1.0 is 100% and 0.0 is 0%. And we can just add it to the percent result as well. So if we want to apply a buff, a 50% attack speed buff, that value would be negative 0.5. If we add negative 0.5 to the percentage, this will be, instead of 1.0, 0.5. And we want to decrease it because we want to decrease the time between the attacks, right? And that is what attack speed is. So again, we just iterate through and apply all these values. And finally, when we are done with all of these and we had no 0 modifiers, we can just return the flat result multiplied by the percentage. So this is the bulk of the whole modifier system. This is the most important thing here, right? So we have these modifiers for each and every property like AD, AP, armor, max mana, and so on. And this is where we calculate that modified number. And to make debugging easier, again, I override the toString method and just display this modifier type and use the enum to have this string here, which can be unit, max health, max mana, attack speed, AD, AP, so on, right? Let's save this with Control S. And the reason why toString is useful here is because the disadvantage of using RefCounted, so let's talk about this for a second, is that it's much less straightforward to debug it in the inspector panel. Because if we were to use nodes here, right, the battle unit would have a modifier handler, which we are yet to implement. Then under the modifier handler, we would have 2, 4, 6, 7 other nodes, one for each modifier, if this was extended from node instead of RefCounted, which makes it pretty straightforward to debug, right? I can just click on it and check the array of modifier values. And this is how we did it in the ModifierValue course. Again, if you want to, you can make sure that this class extends from the node class instead of the RefCounted class. Then what you would do is change those to export variables and you wouldn't need the init. The disadvantage of using nodes for that is that nodes require much more performance, right? Because they add it to the life cycle of the game, they have a performance cost, right? Adding them to the game. And it's not that many, I guess. So in this specific case, that would be 7 nodes per unit. Now, if you have, I don't know, 30 units on board maximum, that would mean 210 nodes. I think most modern computers can handle that performance pretty well, but it's still a trade-off, right? I just wanted to show you an alternative. If you don't care that much about performance or you don't want to prematurely optimize, this can be a node. The reason why I think nodes are not the best, though, is that if you think about what are the advantages of using a node here. First, it's easier to debug. Fair. Okay, that's a good point. But what other advantages you get when you use nodes? You can change them runtime, right? Which means that I can delete and add modifiers on the fly dynamically when the game runs. But do you really want to do this? These are fixed. These are the ones that I already know that the units will have. So I want to add this once, but when do you think it makes sense to delete the AD modifier for the unit in runtime? It makes no sense, right? Because I don't have to delete it. I can just call the clear values method and it stays there, but I clear the values, not delete the whole system itself that tracks all the unit AD changes, right? At the same time, when do I want to add the new one? Can it happen that during the gameplay, when the game runs, I want to add a new modifier that's not there before when I code the game? That scenario to me is not really existent. So the biggest advantage of using nodes is being part of the lifecycle, being able to dynamically remove, add, move the nodes around. And I don't really see where you want to do this with these modifiers, right? These are data that are set in stone, and it's the same when the game starts. What changes is that array of modifier values, right? But modifier values themselves are resources stored in an array inside this. So I don't really see the point of using nodes. The only fair point or criticism against this RefCounted is that it makes it a bit harder to debug because nodes are just there in the remote scene tree, right? It's pretty easy to debug them, but we'll see how we can debug RefCounted as well. So for now, that's my argument for and against using either RefCounted or node. Let me know in the comments what you think about this. It's a valid architectural dispute, I think. But anyways, let's just stick to this solution for now. And we want to do the final layer, which will have to be a node, right? So I want to do the ModifierHandler, which will be added to the unit and does this high-level thing and provides an API, so to speak, a way to communicate between the game and these modifiers. So the final piece of this puzzle, we have the modifier value. At the lowest level, we have the modifier, which represents one of these values and manages it. And if we right-click on the components folder, create a new script, call it ModifierHandler. This one has to inherit from the node class. Click on create and double click to open it up in the script editor. Okay, so what do we need to do at the highest level? Well, first of all, we'll have a class name called ModifierHandler. Then we'll have two variables. There will be an export variable for the modifier types that we want to add to this specific node. So if you think about this, there might be more than one instances where you want to use this system in your game. So right now we only use it on units. And I think this game doesn't really need any other objects in the game where you would apply modifiers. But in other games, you could use this in multiple places in your project, right? So for the modifier types, that's why we have this leading unit underscore, because there might be, let's say there would be item modifiers. It makes really no sense in this game, but if we were to add something like item value and item bonus or something like that, then we would use the same system on units and items. And so the way we make this easy to work with in other systems is we can just create an array of modifier types, and we can populate an array of all the modifiers that we want to add to that handler. So in the units case, we'll add 7 elements to that array, 1 for each modifier type that is present. And so this is used to decide which kind of modifiers we want to create dynamically when the game runs. And we'll have this member variable that actually stores those modifiers. And if you remember, the modifier class itself is a RefCounted object, right? So these won't be nodes sitting in the scene tree, but they will be stored inside an array on that node, the ModifierHandler. So what we do inside the ready callback is exactly that. We iterate through that exported array where we define which kind of modifiers we need, and we use that new keyword to call the init method. You see, if I hover over it, you'll see that it actually calls the modifiers init virtual method, where we have one required parameter, the type of modifier we want to create. So what we do is we create a new modifier for each and every types that we selected and append it to that array. So essentially, when a battle unit gets added to the game and instantiates itself, the ModifierHandler will, during runtime, create all these RefCounted objects for each and every modifier, which in this case is 7 different modifiers. And that's all the setup we really need. Then we can have a bunch of useful public methods we can use to get information from this modifier system and also to interact with it, right? So one such method is querying if we have a specific type of modifier or not, right? This is a Boolean method. We can iterate through all the modifiers, and if the type matches with the one that we want to get info from, we can return true. Otherwise, if we finish the loop and never once return true, we can return false. We can also get one specific modifier, which is super useful when we'll deal with attack speed, for example. So it's a similar method to what we did in the previous one. It's just instead of returning true, we return the modifier itself. And if we don't find it, we return null, essentially saying that we don't have that modifier. And the one final method which is useful is getting the modified value. So this is what we can use to interact with the modifier system from the outside. So we don't have to go down multiple levels. We can just say BattleUnit.ModifierHandler.get modified value, and we can pass in, for example, the base attack speed of the unit and say that we care about the attack speed modifier with the enum and return a float value with the modified value. The process itself is pretty simple. We use the get modifier to actually get hold of the modifier we want, in this case the attack speed. And if we don't find it, if we return null from this method, it means that we don't have an attack speed modifier. In this case, we can just return the base value we had because we cannot modify it. Otherwise, if we did find it, we can return the modifier.getModifiedValue calls result. And if we press and hold Control, this is where we did the heavy lifting, right? So if we did find the corresponding modifier, we can call this value, pass in the base number that we started from, and make sure that we return this new result. So this is where we will communicate with this system. Now, for debugging purposes, we'll also override the toString method. And what I ended up doing here to make it easier to debug is displaying all the information at once. So what I do is I create a packed string array, so I can make one long string at the end, iterate through all the modifiers, and append the modifiers toString to that array, which, if you remember, will return the type of that modifier, and I added this little sign here to make sure it's visually a bit better. And this will display what kind of modifier we are talking about, unit AD, unit HP, and so on. And then iterate through all the modifier values that modifier has and append those to the string as well. And for the modifier value, we have these leading dashes. It will kind of look like it displays under the modifier we connect it to. And when we are done with everything, we'll use the join method and put in the new line character. So all these strings will be separated into different lines, right? This is fully optional. All the toString methods is just, it makes it much easier to test, or if you want to log the data in your game, it makes it much easier to read, right? Okay, that was a pretty long one, but if we save this with Ctrl S, we should have our modifier system ready to go. If you like my content, please consider checking out my Ko-fi page where you can donate one time or become a member and get early access to all my content and videos. Now, how do we test this? The first thing we would have to do is to actually append it to the battle unit, or we can test it in isolation as well. I would suggest first testing it in isolation, which makes everything easier. So let's click on the plus sign here to create a new scene. Click on other node as the root node, and we can just use a node here. Let's double click and rename this to something like modifier test. And under the modifier test, press Ctrl A or click on the plus sign and add a new ModifierHandler node. And you see we have this export variable, so let's add like 3 modifiers. For example, we'll have a max health, AD, and armor. So these are the things that we can modify from this modifier handler. Let's save this scene. I'll just save it in the scenes folder, but we'll delete it anyways when we made sure that it works in isolation. So let's just save this for now. And what we need to do is we need to provide some test data. So let's click on a modifier test, attach a script to it, modifier test.gd is fine. And we can do something like this. So we'll have 3 export variables. We can test it from the inspector with modifier values. We have a reference to the modifier handler. And what we'll do is we'll add the first 2 values to the AD modifier and the third value to the max health modifier, and print the modified value to see if those changes apply, and use 100 as a base value so it's easier to confirm if it works or not. Okay, so let's save this, go back to 2D view, and provide those 3 testing values to make sure it works. Click on the arrow next to empty and create a new modifier value. So test 1 can be, let's say, 25% and percent based, and for the source we can just type in spell1, something like that. For the second value, we can again create a new modifier value, make this 0, so we can test if it turns it into 0 or not. This comes from spell2, and for the third one, we can create a flat value of, let's say, 40. And this comes from spell1 as well. Now, if we save this and run this scene by clicking on this button or pressing F6, if we pull up the output window, what happens is for the first value, for the AD, we get 0.0, which is fine because we should have a 25% increase, but we do have a second 0 modifier, which overrides everything. And for the second one, the flat modifier also works pretty well because we had 100 as a starting point and it turns into 140. Now let's see if we can change this one from 0 to flat, and let's add like 50 to it. So what should happen is, in this case, we have two modifier values. The 50 should be added first, so we end up with 150, and then the 25% gets added on top of it, which should be 187 or something like that. Okay, and if we rerun the scene, it indeed works because it gets bumped up to 150 and then the 25% gets added. But if we bump this up into even more, 100, it's easier to calculate with. Yeah, so we have 200 as a new base flat value and the 25% bonus gives us 50 more. Okay, pretty cool. So it looks like it's working. Let me show you why it's hard to debug. So if we go to the remote scene tree, you'll see that we have our modifier handler. And we have the two arrays, we have the modifier types. One difficulty with enums is that when you use enums in the inspector in this remote scene tree or this debugging panel, they will be replaced with their corresponding number values, which already makes it a bit harder to debug. But if you take a look at the modifiers themselves are RefCounted objects, right? So we don't have them here as nodes, which would be the other solution. And they would be easy to identify based on their node names. So if it was in this case unit max HP modifier and unit attack speed modifier, I should know where to click. But if you don't know the order of these three, which would be 0, 3, and 5, so we can match it to the enum, but since we don't even have the names here, just the numbers, it makes it harder. You have to kind of guess. And I believe 80 was the second one, so if I click on it, I see the data, but again, for the type, I only have a number. And if I click on the values, this was the 80 because it has two modifiers attached to it. So you'll see, I only see remote RefCounted and the object ID. And for the type, I only see the enum number. And if I click on these values, I get these remote resources for the modifiers. And these are pretty self-explanatory. So I do have that percentage value, the source. So I can read this, and if I click on this previous button, I can see the flat value as well. And if I go all the way back, I can click on this other modifier, but you see that I already messed up because I wanted to show you the max HP one and I clicked on the other one. So it's kind of hard to tell which one is it. And this takes up a lot of time from your debugging if you have to sort of dig through this like that. So hopefully you can see the trade-off. This is a more optimized version, and it makes no sense to make these nodes in terms of how we utilize what we get from nodes, but for debugging purposes, it's much easier, or it would be much easier. Now, this doesn't mean that we cannot provide an alternative way to quickly get the information we want when we test the game. So one thing we can do is if we go back to the ModifierHandler script, this is where tooling and making tools to test and debug the game come in handy, right? So if you were to make a big commercial game, spending time on tooling, debugging tools, and editor tools that you can use as a developer sometimes feels like wasted time. But if you think about how much time you would waste checking modifiers in your game and trying to walk through that RefCounted nightmare, this is time well spent if done right. So the most primitive version of this, I don't really want to get into tooling right now, but we did override a bunch of toString methods. So the most primitive version of this would be to override the input or the unhandled input virtual methods and say that when we press a specific button, just print the toString methods output to the output console, right? Because we did this toString override for all three classes. So with this little change here, it becomes almost trivial to debug this, because if we run the same scene again, you'll see I have the numbers here, but if I press Q, test one, in this case, this is where we have our toString method code, and this is pretty straightforward to understand, right? For the max health modifier, I have one flat. I can see the source, I can see the value. For the 80, I can see both of them. I have a flat for 100, and I have a percentage for 0.25, and I also get the sources. So with this button press, I already have all the debug information I want, which makes it easier to test. Of course, if I want to change something, I still have to walk through this in the remote scene tree. So this is just to display the information I want, but tooling can get around it, right? So I don't really want to spend too much time on it, just kind of wanted to show you that it works and it can be debugged as well with the RefCounted solution too. But I completely understand if someone would much rather add the 7 nodes to each of the units, right? I would say that for most modern computers, this wouldn't be a problem. But sometimes if you think about, for example, mobile game development, performance suddenly becomes much more an issue, right? So for mobile games, you want it to be as optimized as possible, not just for FPS gains, but also for battery usage, for example. So I just wanted to talk about this, open a discussion, and present an alternative to this. I still would say that I'm much happier with the RefCounted version, despite the fact that it makes it harder to debug, probably. But in isolation, you can see that it works. So after we are sure that it worked as we expected to, we can get rid of the testing code for now. And we can also delete this testing scene we have. So let's search for modifier test. And both of these files can be deleted if we're sure that they work. But we do have to hook this system up with the BattleUnits. So that's the final thing we need to do before we can actually move on to trait bonuses. So with the BattleUnit root node selected, click on a plus sign or press Ctrl A and search for ModifierHandler. Double click on it or press Enter and drag it up to its place. One thing we need to do with this is set up the export variable so we have all the modifiers we need. The size will be 7 in this case, and we need to select the different modifiers we want to apply, basically selecting each and every one of them, like so. Now, this will create the according RefCounted objects. The really final thing we need to do to hook this up is to actually reference this as an already variable inside the BattleUnit, so we have outside access when we need to. Click on the script icon here, scroll all the way up, and drag ModifierHandler over, press and hold Ctrl while releasing the mouse, and use Alt plus up arrow to move it to its place. And now we officially have access to the ModifierHandler, so when we add trait bonuses or do whatever we want to in the game, we can apply modifiers to those values. Let's save this with Ctrl S and move on to the final part of this episode, which is actually creating bonuses and hooking them up.